Hi everyone and welcome to this new video about power factor correction. That is our example number 5. In this example we will consider a really detailed situation and also a practical situation. We have a following given. There is a factory which consists of the following loads. I will discuss them shortly, and it's connected to 1 kilowatt RMS voltage source operating at 50 Hertz. And the loads are also in parallel, so it's also important to note. What do we have? We have a heating system which absorbs 40 kilowatts with a power factor of 1 unity. There are some induction motors which absorbs 20 kilowatts with a power factor of 0.6 lagging. And there are also systems for lighting, so we have therefore 8 kilowatts absorbing and with a power factor of this time 0.8 but leading. Okay, what are the questions? And this situation is actually sketched here, as you can see. So we have the power, the voltage source with 1000 volts RMS 50 Hertz operating, 3 loads in parallel, load 1, load 2 and load 3. So it is 40 kilowatts with a power factor of 1. We have load 2 with its own true power, and also for load 3 in the same manner. So what do we have? The following questions. Calculate the required parallel element to make the power factor unity, so PF of 1 for the complete system. And the second question is, calculate the supply current, so the current that must be supplied by the voltage source Vs, both for the uncompensated and compensated system. And we would like to compare the results. Okay, let's start with the situation for question A. The situation is as follows. We have 3 loads, so we can actually say the following about this and make maybe also a table. So we have the load and the load 1, we have the load 2, and we have load 3, and we can make a table to see the situation in more detail. So what do we have? Now, there's for each load the true power is given, so this is actually the P, and for each load is also the power factor given. So if I write down for load 1 what the true power is 40 kilowatts, and power factor is 1, and for induction motors for the load 2 is 20, but it is 0.6 lagging, so 0.6 lag. And for the third one it is 8 kilowatts, and we have 0.8, but this time leading. Okay, now we can make a sketch for each load, so a power diagram that will also illustrate the concept in more detail. So let's do that also. So I will make a sketch for the load 1. This is the real part, this is the imaginary part. What do you observe for the load 1? There's a unity power factor. That means actually the reactive component is 0, so there is no reactive power. The apparent power will be equal to the real power, so I only have a arrow for the real power, so that's actually for P1. I will denote it as P1. So there is no Q1, there is no actually a different S1, so there is no phase in this situation. So if you continue this for load 1, so let's make this clear. This is for load 1. So I will make this also for load 2. What do we have for load 2? Now we know that is a lagging power factor, so I know already that the phase is positive. So that's actually the very important information. So I know also there is some reactive power here. So if I have P2, there will be also, I'm going to make it in green, there will be also some Q, and it's time Q2 to designate the situation for load 2, and also associated S of 2 and its own phase. So let's make this theta 2. Okay, so this is theta 2. Let's make now the situation for load 3 in the similar form. So I have the real and the imaginary parts, and this time I know the reactive component must be pointing in the negative y direction. Why? Because the leading power factor, and leading power factor means the phase, the theta associated with the system is negative. So I have again some real power, which is P3 in this time, and there is the reactive power Q3, but it is pointing in the negative y direction. So that's actually interesting to note in this phase. So in the first place, you have to actually recognize that the situation for all of the loads are as follows. So this is a very handy sketch to start with. So what we would like to know is what is the parallel element required for question A, such that the complete system has a power factor of equal to 1, a unity power factor. Do I know actually that I require here a capacitor or an inductor? At this stage, I cannot assume it is a capacitor for sure or an inductor for sure. I don't know that yet, but I can already say it might be a capacitor because this part is larger than this part. That is actually what I sense, but I'm not sure about that. So let's continue with the calculations. For all of the loads, I would like to calculate and denote the real powers, the phases, and also the P's and the Q's and the S. So I will do that for all of the loads. So let's start with the situation for load 1. So what do we have? The situation for load 1 is as follows. We have a PF1, which is 1, and this will result in a theta 1 of 0. That's just for completeness. And the P1 was given as 40 kilowatts, and since the theta is 0, Q will be 0, so 0 volt amperes reactive, and this will be also equal to S1. So the S1 for the load 1 is also equal to P1. Okay, let's move on for the load 2. What do we have for load 2? We have a PF2 is equal to 0.6 lagging. This will mean that the theta 2 is our cosine of PF2, which will be positive. So if you substitute the value in that formula, our cosine of 0.6, you will get approximately 53 degrees. Now, using again the formulas for Q2, which is of course equal to the value of the P2, we know from the geometry, times the tangent of the theta 2, again substituting the values, you will get 26.7 kilovolt amperes reactive. Now, in a similar form, you will have for S2 have the P2 divided by the cosine of theta 2. Again, using the geometry, and you will get here 33.3 kilovolt amperes. Okay, that's for the complete situation for load 2 only. Again, this is all done using the geometry. For example, if I want to know how to express this, you can see for this length is the vertical here, and this is the horizontal. So I can use a tangent. I make the vertical divided by this side, the horizontal part, and I will get Q2 divided by P2 is a tangent of theta 2. I will get this by rewriting this expression. So let's move on for the third load. So PF3 is 0.8 leading, and I know already that the phase 3 will be negative, so I will have a minus arc cosine, which will be PF3. So if I substitute those values here, I will get, again, rounding off, minus 37 degrees. Okay, that's actually for this situation. And what do I have for Q3? Q3 will be P3 times the tangent of theta 3. Again, substitution values, you will get exactly 6 kilovolts amperes reactive, and for S3 you will get P3 divided by the cosine of tangent 3. I mean the cosine of the theta 3. So you will get exactly 10 kilovolts amperes. Okay, that's actually for this situation, for the last load. And remember, the P2 here is already given 20 kilowatts, and for this one it is 8 kilowatts. So let me make this also clear for the load 1 and load 2 and load 3. So this P2 is 20 kilowatts, and for P3 it is 8 kilowatts. Okay, I'm now actually in general done with the situation. I would like to know what the total system is. So what is the total system all about? The total system is of course the summation of the real parts and the summation of the imaginary parts, and I will have of course a factorial sum of them to get the total apparent power. So let's look at the situation for total system. So let me write down the total system. So what is the total system? So total system will have, of course, the S of total, which is equal to P total plus or minus, we don't know yet, depending on the value of Q, but we will start at the plus, we can always change it, plus J Q2. So this is actually the general formula for the apparent power. And what do we know about the P total? Now, P total is the summation of P1, P2, and P3. So what is P1 and P2 and P3? This is actually 40. So 4 times 10 to the power 4 plus 2 times 10 to the power 4 for the motors. And for the lightning you have 8 kilowatts. So we will have in total 68 kilowatts. That's actually for the real power. Okay, let's move on for the Q total. What is Q total? Now we have to be very careful for Q1, and you have Q2 that you can add them together, but for Q2 you already know there's a negative sign here. So you have to be very careful and make this a minus sign, so you will have minus Q3. Okay, what is Q1, what is Q2, what is Q3? We already calculated this, it's all here. So Q1 is 0, Q2 is this one, kilovolt amperes reactive, and I will get the 6 here. Of course, I will make it minus for Q3. So what do I have? I have the following: 0 plus 26.7 times 10 to the power 3 minus 6 times 10 to the power 3, and I will get 20.7 times 10 to the power 3 volt amperes reactive. And look at it, this is a positive Q, that will mean inductive. So if you have an inductive system, inductive circuit in total, that means actually to compensate this, to make this power factor equal to 1, the only way to do this is using a capacitor. So I have to use something else which compensate this situation. That's only possible using a capacitive element for compensation. So I can already say to get to power factor of 1 I need a capacitor, so I can use the following situation for capacitor element, which is the compensation, must be equal to the Q total to compensate those Q's, which is of course equal to 20.7 times 10 to the power 3, and that's volt amperes reactive. Now I know if I now place this parallel component across these 3 loads, my load will be connected here actually, and this will have of course the same voltage. So all again 1000 volts RMS at this same frequency. So what can I say about the reactance? I can use the formula again for Q is equal to the volts squared time divided by the reactance. So I will have the following: the Q of the compensation capacitor will be equal to the voltage source in the RMS value squared divided by the reactance of the capacitor. Okay, now I know this is 1000 squared, and I have this one calculated from this Q total, and I have the Q of C using the formula. So I will get the following: 20.7 times 10 to the power 3 will be 1000 whole squared divided by Q of C, and if you have done the math correctly, you will have the Q of C of 48.3 ohms. This is actually the amplitude of the Q of C. Now using the already known formula for Q of C to go from the Q of C, I mean the X of C to go to the capacitor value. So x of c will be equal to 1 over the omega c times c. So I will have the following. The c will be 1 over omega times x of c. So this will be 1 over omega. What is omega? Omega is 2 pi times the frequency. The frequency was 50 hertz, which was given here in the question, also in the text. So I will have 2 pi times 50, which will be 100 pi. I will write it down to make sure that you see the frequency also here. So it's 2 pi times the 50 times 48.3, and I will have approximately 65.9 microfarads. That's actually the capacitor required for this question, for question A. So if I place a parallel component, let me sketch this. If I have the 3 loads here, so I will make this Z1, Z2, so for load 2 and for Z3, so I will have the voltage source connected across them, and this is the voltage source Vs, and the red one which will place across the complete system, and this is the capacitor I have just calculated, C, which has a value of almost 66 microfarads, or 65.9 microfarads. Okay, that's actually for question A. Let's move on now to question B, which is about the compensated and the uncompensated system, and we would like to know what is the current, because if you want to know what the supply current is, which is an important part of the total efficiency of the system, so because the system, this circuit, will supply a voltage, and also due to the loads will also require some current, so that will also determine the total apparent power. So if I look now to the uncompensated system, so uncompensated situation or system, so no compensation in place. So what is this? What is the situation? We have, of course, the S total, which is the square root of the P total plus the Q total squared. It is again not compensating. So what is the situation? The P total we have calculated here, which was 68,000. So if I substitute those values here, I will get 68,000 all squared, and I will have plus this value, that's the Q total, which will be 20,700 all squared, and I will have a apparent power of 71,081 volt amperes. This is actually for situation 1, actually for situation without the compensation. So what is now the supply current? So let's calculate it also. So supply current IS will be the apparent power divided by the supply voltage in RMS, which is already given in RMS, so you don't have to do the square root of 2. So what we have is the following: 71,081 divided by 1,000 will give us 71.081 amperes in RMS. So it is approximately 71 amperes. Now let's look at the situation with compensation. So compensated system. Now in the compensated system, that's actually why we compensated, you lose your Q. So actually you only have the real part of the system, which is actually the required situation, because you want to deliver the total power to the resistive parts of the system. So what you get is that the S of t, so the compensated situation S of t, I will make it with a prime, this is a new situation. So S of t will be equal to P of t, which is just 68,000 watts. Okay, so the Q total, I will make this clearer, so the Q total is here 0. Okay, that means the IS, of course this is for the prime situation, so for I source in the compensated situation is the apparent power for the compensated situation divided by the supply voltage, which is actually the same value. So what you get is the following: 68,000 divided by 1,000, which is 68 amperes. So the change, what you see is the following: if you reduce your supply current from 71 amperes to 68 amperes, so your change in change in the supply current IS is the following: delta IS will be IS minus IS prime, which is 71.81 minus 68, which will give us 3.081 amperes, all in RMS value. This is of course also in RMS, the second situation. So what you see is the following: you will win actually this much current, or you will not have to supply this much current. So this is actually also an efficient situation. That's actually the whole objective of correcting the power factor and going to as close as possible to unity. That's actually the whole business about correcting the power factor. So in this example we have looked at the two situations. One is the uncompensated and the following and the compensated system. We have also calculated the required value for the parallel element, and we have also determined it must be a capacitor. And why is it a capacitor? That's also very important. So that's actually for this example, example number 5. As you can see, it's a little detailed example, but it will give you a lot of background and also why we do some specific steps. So follow this video if you want to learn more about it, and also look at the other examples to see how we did with other situations. So of course we will continue with other examples and other topics in this and other situations. So keep in touch and don't forget to share and to like, and I'll see you next time, and have a nice day.